We've learned that there are 7 strong acids, and by definition, a strong acid is one that is going to completely ionize in an aqueous solution. And since they completely ionize, then the concentration or the molarity of the acid is equal to the hydrogen ion concentration or hydronium ion concentration. For example, if you start with 1 molar HCl and it completely ionizes, then it's going to produce 1 mole of hydrogen or hydronium ions, as well as 1 mole of chloride ions. So, for a strong acid, monoprotic acid, the concentration of the acid or the molarity is going to be equal to the hydrogen or hydronium ion concentration. There are 8 strong bases, and they are the soluble hydroxides. Remember, an insoluble compound in water is not going to solvate and produce ions, but our soluble hydroxides are going to be the group 1 alkali metal hydroxides, which are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, as well as the heavier group 2 metal hydroxides, which are calcium, strontium, and barium hydroxide. And since these are strong bases and they completely dissociate in aqueous solution, then if we know their molarity, then we also will know its hydroxide ion concentration. If we were to write an equation for the dissociation of an acid in water, it would look like this, where HA is the acid, A is just denoting whatever anion happens to be bonded to the hydrogen. And so once the acid ionizes, then the ion is left as a product by itself, aqueous, and the hydronium ions or hydrogen ions that are formed are left also on the product side. And so we could write an equilibrium expression for that with products over reactants raised to the power of the coefficient, just like we did in the previous chapter. And this K is given a special name, Ka, because it's the dissociation constant for an acid. Here we have a table of dissociation constants, and notice that these are all weak acids. None of them are on the list of the 7 strong acids. For a strong acid, because it's going to completely ionize or dissociate in water, the value for Ka would actually be infinite because it completely dissociates, and there's nothing left of the species that would have been on the reactant side. So these are all considered to be weak acids, and the Ka values, the larger Ka values here, are going to go along with the stronger of the weak acids. Compare that to the really tiny Kas. Very, very little of these acids are going to ionize. And so we're going to end up, when the equilibrium is reached, with most everything on the reactant side, the phenol and the water in this instance, and very little on the product side, hence a very small Ka. Comparing that to something like hydrofluoric acid, which will ionize a bit more into hydronium and fluoride ions, giving us a much larger value for Ka. So the trend is going to be, or the interpretation of this is going to be, the greater the value of Ka, the stronger the acid, the more it's going to dissociate into hydrogen ions and its anion. The more hydrogen ions it's going to have on the product side, the greater the value for Ka will be. In this unit, we're talking about acids and bases. And so what we're going to do is determine how to calculate a Ka if we know the pH of a solution. So formic acid is a weak acid, and when it dissociates in water, it's going to form formate ions and hydronium ions. And if we wrote the equilibrium expression for this process, it would look like this. And remember that the hydronium ion is the same as hydrogen ion, and so if we can determine the hydronium or hydrogen ion concentration, that gives rise to the pH. So we can use that information pH of the solution to determine the hydrogen ion concentration to plug into our equilibrium expression. Going back to the problem, we're told that the molarity of the solution is 0.1 molar and that at 25 degrees Celsius, its pH is 2.38. And if we know the pH, we can then determine the hydrogen ion or hydronium ion concentration. Since pH is the negative log of the hydronium ion concentration, and the pH is 2.38, in order to solve for the hydronium ion concentration, we're going to take the antilog of the pH, or 10 to the negative 2.38, which is going to give us our hydronium ion concentration, which is going to come out to be 4.2 times 10 to the negative third. And since for our acid, every hydronium ion that is formed from the dissociation of the acid is also going to form a formate ion. And so then the concentration of the hydronium ions will be equivalent to the concentration of the formate ions. So we need to use an ice chart, and from the problem we know that our initial concentration of the formic acid is 0.1 molar and our initial concentration of our products is going to be 0. And we know that at the change this formic acid is going to decrease by some amount as it dissociates, producing hydronium ions and formate ions. And since we know what the pH of the solution was, and we used that to determine the hydronium ion concentration, which we found to be 4.2 times 10 to the negative third. So we know that the hydronium ion concentration increased by that amount. And since when formic acid dissociates, it's going to form one hydronium ion for every one formate ion, then the concentration of our formate ions at equilibrium is going to be the same as our hydronium ion concentration. And since this is a 1-to-1-to-1 ratio, whatever amount the species increased by, this species has decreased by. And when we subtract, we will find that at equilibrium we have 0.095, which in terms of sig figs will actually round to 0.10. And then we just plug our values into the equilibrium expression and we solve for Ka. We can also take this a step further and calculate the percent ionization of the acid. And remember that a percent is simply the part divided by the whole times 100. So if we want to know the percent ionization or the percent of hydrogen or hydronium ions that formed, then we would just take that part, the hydronium ion concentration, divide that by the initial concentration, that was the acid before it ionized, and multiply that by 100. And so you can see that our percent ionization for that acid is 4.2%. That means it's a pretty weak acid. We can also do the reverse of what we just did, and that is to calculate the pH of the solution if we know the Ka value. And here's the equilibrium equation for acetic acid. An acetic acid in water is going to dissociate to some degree, forming hydronium ions and acetate ions in a 1-to-1 ratio. So we're starting with a molarity of 0.30 molar, and we're given the Ka for acetic acid, and so from there we want to determine the pH. Now remember, in order to determine pH, we need to know the concentration of hydronium ions in solution. Here's our expression. Now we're going to need an ice chart. So given that we're beginning with 0.3 molar acetic acid, and we know that it is going to decrease by some amount, let's say X, that means that our hydronium ion concentration is going to increase by some amount, X, and our acetate ion concentration is also going to increase by some amount X. And so at equilibrium, we have, when we subtract 0.30 minus X, X, and X. Now, since we know that we have a very small value for Ka for acetic acid, what we're going to do is we're going to ignore this minus X because we know that in terms of sig figs, with our Ka being so small, that amount will be negligible. So then we just plug our values into our equilibrium expression, and that will give us our hydrogen ion concentration. And once we know the hydrogen ion concentration, from that we can determine the pH, which is the negative log of a hydrogen ion concentration. So we'll have a pH of 2.64. And that's it for now.